yeah, agreed to come give us this seminar. So Lelievre is professor at the National School of Roads and Bridges, which it made them laugh because it's the reference school for French civil engineering. And his really and Benjamin done a multi-scale also Louis, and a postdoc at the University of Montreal. HDR on mathematical and numerical analysis of some molecular materials from the microscope scale to the macroscope scale. Oh, sorry. And he did a sabbatical at Imperial College of London. So he is a professor at École Nationale des Ponts et Chaussées, if you want to be serious. and so he is a great expert of heard his talk and really fascinated by this, so I think you will be too. Please.
Merci. Est-ce que ça suffit ça comme micro en fait? Ou ce micro-là suffit en fait? J'ai pas besoin de ça en plus? Ok, parfait. Ok, ouais. Merci. Thanks a lot for the invitation. It's really a pleasure to be here. So we discussed by email with Stefan about the subject of the talk. So I did computational fluid dynamics years ago, but I more or less stopped about 10 years ago maybe, or so I didn't want in front of the audience to take a chance and go back to old subjects. So we are discussing with Stefan offline of the generalized Navier boundary conditions and things like that. I've been working also on viscoelastic fluids, and so actually I entered this topic of molecular dynamics through this way because I was studying viscoelastic fluids, the viscoelasticity coming from the fact that you put polymers in the fluid, and so this modifies the behavior of the fluid. And so I've seen the Doyer words here, so I was reading all these books at that time, and so I dig into molecular dynamics, which is really how the polymer moves. And I basically never came out of that. So because it's so this will be a little bit about how we simulate the matter at the scale of the molecules. Okay, so this has some applications to liquids and fluid mechanics, of course, but it's really about MD, and in particular about one of the main challenge in this context, which is how to bridge the scale between the time scale at the atomistic level, which is the order of the femtosecond, 10 to the minus 15 second, up to our scale. And so this time scale is really one of the major challenge, and it's related to what is called metastability. Yeah, so how long I'm supposed to talk? I mean, it's perfect. Okay, I don't want to to take more time of what. So all this started with discussions with colleagues from Los Alamos National Laboratory, who proposed some numerical methods to sample metastable dynamics, and in particular molecular dynamics for materials. And we wanted to understand a little bit how it works. So then we worked with colleagues that I'm listing here, mathematicians on these subjects, and these are some students with whom I've been working on that over the past years. So, and there will be a central object which is called the quasi stationary distribution. So I will explain to you where does this come from. So what we would like to do with MD is to simulate the matter at the scale of atoms. So it has applications in chemistry, in physics, in biology. So we are working, for example, with Sanofi on drug design, with colleagues at EFPEN on catalytic reactions. In this context, it's something that Arthur Voter, our colleague from Los Alamos, has been working on, which is the diffusion of add atoms on the surface. So you have three levels here with the colors, represented with the colors, and you would like to understand at which scale the upper atoms, the yellow ones, diffuse to the border. And you see the time scale, it's microseconds, and so you have to do something if you want to simulate these kind of things. you cannot do it naively. Okay, so you have to do a trick, and I will explain a little bit the kind of tricks you can use. So these simulations consumes a lot of CPU, and compared to fluid mechanics, I would say that maybe it's not completely justified in the sense that this is a quite recent field in terms of numerics. So people are basically doing brute force. Okay, so it consumes a lot, but it doesn't mean that it's very always very smart in the way people are using the models. It's basically you take the atoms, positions, velocity, Hamiltonian equations, and let's go for for just integration of the Hamiltonian dynamics. Okay, so of course it costs a lot, and the mathematics really came recently in this field, and so people are trying now to think how to do simulations efficiently, and this is part of our job to try to think about that. What are the main challenges? Maybe compared to fluid mechanics, there is one which is the modeling. So I think that for you also you have modeling problems, but one of the ingredients that we have in molecular dynamics is the model of the interactions between the atoms. It's called the potential energy, and this interaction is not very easy to decide. In principle, you have to go back to quantum, to Schrödinger equations to compute the electronic ground state for given positions of the nuclei. This is very costly, and so people have to use empirical force fields or some approximation of the Schrödinger, of the solution of the Schrödinger equation. And this has some, implications on the quality of the model, which is not fully understood. And for example, modeling water is not easy at all, because you have many effects which are not easy to model. There is, of course, this big, trend of using machine learning techniques to try to improve the models and to incorporate data, more generally, experimental data. And that's one way to go. And these so-called machine learned force fields are now more and more popular. And so over the past 2 or 3 years, there have been really breakthrough in that direction. What I will talk today about is really about the third aspect, which is about the sampling. So we are at a scale which is very small. So what we would like to do to go to our scale is to do averages. So we have to do many simulations or to integrate over a very long time in order to go from the microscopic to the macroscopic. It's basically doing statistical physics numerically, okay? And again, if you do it naively, it costs a lot, okay? And this is a small picture that I took from Danny, again, our second colleague at Los Alamos, where he represents on the x-axis the time scale that you can reach with, let's say, naive MD, and on the y-axis the number of atoms that you can simulate. And if you have, computers which are more and more powerful, it's quite easy to increase the number of atoms, because basically you can parallelize the computation of the force field in a very naive way, like domain decomposition. You compute the interactions within the boxes, and then between the boxes, and basically you can scale up the number of atoms with the number of CPUs you have access to. For time, it's different, because time is a sequential in nature. So when you want to when you increase the number of CPUs, it's difficult to increase the number of time steps, because it's sequential in nature. Okay, and so there is a kind of barrier here that it's difficult to go through. At least with naive MD, it's not possible to go beyond the microseconds, basically. Okay, which is already quite heroic in terms of time scales. And so in the background there is this time scale problem which is everywhere, and so people are trying to find ways to go beyond that, and I will talk about one way to do it in this talk. Before I go into the details of this subject today, which is this sampling of metastable dynamics, I wanted just to go through a few other topics that we are working on, in case it rings a bell. There is a question which is about the rare event sampling. So there are rare events which are related to this timescale problem. Observing a transition between metastable states, as you will see in the following, is a rare event. So, for example, I'm working on algorithms which are also used in statistical hydrodynamics by Freddy Boucher to go from one, conformation of a system to another one, a hydrodynamic system. And so these rare event techniques are used in this context in MD to see transitions between metastable states. And so this is one of the keywords of the numerical methods we are working on, these rare events. There is also this question of constraints. In many situations, we add constraints on the system, so we have actually measures, probability measures, which are supported on manifolds to sample, and this creates specific problems that we have to deal with. That's another. There is a question of effective dynamics, which is also in the background. So we have typically many atoms, and people are only interested in a few of them because only a few of them describe the conformation of the system. And for example, if you think of a defect in a material, only the position of the defect matters, basically, okay? Or maybe of the defects, if there are many of them. So there is a question of trying to find effective low-dimensional dynamics from the full, okay? And typically in the polymer physics I was mentioning before, people are playing a lot with this. You have the full polymer, and they would like to find some kind of effective dynamics on the end-to-end vector, okay, which typically gives you the conformation of the polymer, orientation on length. And so actually, yeah, when I started to work on this, I really worked a lot on this, trying to see, for example, if the free energy is a good proxy to derive an effective dynamics is a big subject in itself. There are questions about non-equilibrium steady states and again machine learned force field. But today I will really focus on this metastability problem, and this is what I would like to explain now. So this is a quite old paper, but it's not the question. The question is just to illustrate what I would like to do. So you have a protein here, a peptide, which evolves, and here we represent the conformation of the peptide using only two collective variables. So whatever it means, two measures, two things that you can measure in the system to represent the system. And here, these colors represent the probability to observe the system at a given value of these two coordinates, two collective variables. And so you have here wells, you see, where the system can be trapped. And when you see these kind of pictures, the idea is that probably it will take a lot of time to leave such a well, to go to another one, and then to another one. But probably the wigglings inside a well will not be very important because nothing happens really. So what will matter really is to simulate what happens on long timescales which are long enough so that you see transition between the metastable states. Okay, and so this is really the story that I would like to tell today. So how we will be able to, go from a dynamics which will spend a lot of time inside the wells to something which will just jump between the wells. Okay, so this will be a theoretical part in some sense, and then I will explain how it can be used numerically to accelerate the sampling of these dynamics. Okay, without destroying the dynamics itself. That's the big subject. We are really interested in this molecular dynamics in the way things are evolving. Not only the thermodynamic properties, not only the relative probability of these different ways, but also the way you move from one to another one. So what are the equations? So the basic modeling ingredient is a potential function V, which to the positions of the n atoms, so D will be here 3 times the number of atoms, associate an energy. So as I told you before, in principle, this V should be computed as a ground state of your system for given positions of the atoms. In practice, people are more using, some kind of proxy to that. But for us, in this talk, it will be given to us. It's a potential V which is given, and we would like to do dynamics with that. And we can do two types of dynamics: dynamics which are in the full state space, of all the positions of the atoms, or dynamics which will be some coarse-grained version where you will just jump between some state. Okay, and what I would like to explain is how we can make a link between these two worlds. Okay, the continuous state space Markov dynamics that I have in the beginning, and here a coarse-grained again, Markov process, but with values in a discrete state space, state 1, state 2, state 3, etc. Okay, so that's the idea how to make a link between the two. And so let me start with two models. So let me start with the first model, which is a model which involves the positions, or maybe the positions on the momenta. So Q here contains all the positions of the atoms. P contains all the momenta of the atoms. And if you look at the equations which are here, and you set gamma to 0, you basically have the Hamiltonian equations. The derivative of the position is just the velocity, inverse of the mass times momenta. And the derivative of the momenta is the force, and the force is minus the gradient of the potential. Okay, so that's really an energy, a dynamics which conserves energy. Okay, then this is not used a lot in practice because as soon as you have a temperature in the system, you have to model in a way the interaction with a bath. Okay, which will fix the temperature. So it will fix the energy on average only. Okay, so this is done through typically a thermostat, and one which is very popular is called the Langevin thermostat. It goes back to Langevin, to one of the papers of Einstein. So you have a friction which is minus gamma the velocity, a viscous friction, and then you have noise plus square root of 2 gamma, beta minus 1. Beta minus 1 is kBT, it's the Boltzmann constant times the temperature, times the Brownian motion. Okay, so these two terms are here in order to make the dynamics ergodic with respect to the Boltzmann-Gibbs measure which is there. So if I do an average over positions over time, I get an average with respect to exponential minus beta v, okay, which is what you expect if you know in this so-called canonical ensemble, thermodynamic ensemble. There is a version of this which is a little bit simpler to analyze mathematically, which is obtained when you send gamma to infinity. Basically, the velocities are always at equilibrium, okay, with respect to the kinetic part. And so you have a dynamics only on the positions, which are given by this so-called overdamped, which is quite simple to understand, I guess, because you just have a steepest descent. So you take a point, you follow minus grad v, so you go down the energy, and then you add noise, okay? So I think it's quite intuitive to see what will happen. You will start from a point, you will go to around the local minimum of V, and then you will wiggle there, and then you will go, thanks to the Brownian motion, to another minimum. Okay, so this will be typically the behavior of this. This is called metastability, and I would like to just illustrate this on two simple drawings. So here is exactly what I described. You have an energy, function in 2D to make things simple here, where you have a system which will go to around a local minimum, and from time to time it will jump and go to, it will, make a transition from the left well to the right well. And if you plot as a function of time the x coordinate, you really see this metastable signal you have for a very long time around -1, and then you go to 1, etc. One thing we should keep in mind is that in high dimension, you also have entropic effects which create metastability. So in this situation, you see you are trapped in a domain which is very large compared to the exit doors. Okay, so you are in this room in high dimension, and the exit doors are very narrow. So again, it will take time to leave, but because of a different phenomenon, it's related to the fact that you don't have to go over a barrier, an energy barrier. You have to find your way, to the exit door. And so these two phenomena are combined. So this is an entropic trap. This is an energetic trap. You are in high dimension. You don't know exactly where to go to leave the state. Okay, and so it's a bit nightmarish. And so the naive version is just to discretize the dynamics I've presented before. Okay, and to wait for them to leave the metastable states. Okay, and if you want to discretize these dynamics, typically you have to use a time step which is of the order of the vibration of the stiffest bonds, which are the covalent bonds, and this is the femtosecond I was mentioning before. Okay, and typically the transitions can be of on nanoseconds or more. Okay, so this is where the difficulty is. On this transition between metastable states, these are the so-called the rare events of interest in this context. So just to give you a very simple system where you can visualize things in maybe higher dimensions. So you have 7 atoms. They interact through a Lennard-Jones potential. Okay, so the Lennard-Jones potential, probably you know it. So as a function of the distance between two particles, you have a steep increase of the energy for small distances, okay, and then you have an equilibrium distance, and then you have something completely flat for the potential, okay, and you make a sum of all the pairs here, okay, and so these are the four. In this simple 2D case, we know exactly the four local minima of the potential V, which are represented here, of course, up to renumbering of the particles. And this is what you observe if you simulate this kind of system. On the left, upper left, you see. So it's really what I was saying before. I guess in the ball eye norm, you see that the system remains trapped for a very long time around some local minimum. Okay. So here is a global minimum actually of the system. This is obtained by just doing a steepest descent from there. Okay, at each time step, just to visualize things. And you see that you spend a lot of time around this local minimum, and from time to time you jump. Okay, so this is the energy. So this is the energy of this, and this is the energy of that, as a function of time. And just to visualize the different states. So here you're trapped in the global minimum, and then you will see jumps from time to time. So here, this is basically what you would like to simulate. You would like to see when you are in a state, how long you stay in a state, and where you will go afterwards. Okay, that will be the information that you need. Okay, it's called the state-to-state dynamics. You see that sometimes you go to a state very quickly and you go back. Okay, that's one behavior. But most likely, when you go to a state, you will stay for some time there and then jump to another one. Okay, and this is a naive simulation. Where we just discretize. And the question is, can we use a trick in order to get this much quicker than by just simulating the whole system and discretizing time and just doing the naive simulation? That's the kind of question that we would like to discuss here. Any questions up to now? Is it clear what we would like to do? Okay, so how to model a little bit what we would like to do. So, yes. So the interactions here is really you have it's an energon, so you have V. So you have Q1, Q7, and then the V of Q is just the sum over all the pairs of some curly V, let's say QR minus QJ, and this curly V is there is a 1 over R12 and there is a 1 over R6. This is R, and this is the curly V of R. Okay, so that's just very simple energons. Okay, so the picture is the following. So we have some domains in RD, so you can think of the basin of attractions of local minima, in which you will remain trapped for a very long time. Okay, so I call such a domain curly O, and then there is the curly S here, which is the associated states where you have the positions here and the momenta. So it's a cylinder, if you want. Okay, in phase space. And so you enter such a state, and you stay trapped for a very long time. And the problem is the following: how could I guess when and where I will live in the future? Okay, so this is called the exit event. I would like to understand the first exit time from O, and I would like to understand the first exit point on the boundary. Okay, that's what we would like to look at. And again, you can think of O as the basin of attraction of one of the local minimum for this steepest descent. And the idea is, the question is, can we build just a jump Markov process to simulate this exit event, to simulate this pair of random variables? Okay, if we were able to do that, we could simulate much quicker this tau and x tau, and so we could go much quicker to large times. Okay, so that's the question we would like to look at. So this has a theoretical counterpart because it's a way to justify such so-called Markov state models, so jump models between the states, and also numerically, as I will explain in the second part of the talks, in order to again to simulate more efficiently the state-to-state dynamics. And this is related to the algorithm that Arthur Voter and Danny Perez proposed. So in order to make the link between these two worlds, so the Langevin dynamics and these jump Markov models. Let me explain in one slide how these jump Markov models work. So you have your domain O. The idea is that you make a partition of the boundary as a function of the neighboring states. So through DO1, you will go to a first neighboring state, here another one, etc. Okay? And the way these so-called kinetic Monte Carlo or Markov state model works is the following. You introduce rates to live through each of these possible exits. These are the k's. And then the exit time is exponentially distributed with parameters the sum of the k's. And the exit region will be I with a probability which is ki over the sum of the kj. So basically, if a jump Markov model is correct, you have two random numbers to draw in order to get the exit event. So it's very, very efficient. One which is exponential law here, and one which is the exit region there. And the two are independent in addition. So it's really, really easy to use. So if such a model is correct, we should use it. I didn't make precise what are the k's. So typically the k's are given by, so these are so-called transition rates, are given by the Ihring-Kramers formula that maybe you already seen in chemistry or it's Ihring-Kramers, Arrhenius laws and this kind of thing. So you have a prefactor time exponential minus beta, an energy barrier. Okay, so this will of course not work for the entropic barrier I was mentioning before. Okay, as a purely entropic. But for an energetic barrier, it is believed that this is a reasonable approximation. You measure the difference of the energy between the minimum of V on the boundary, on the part of the boundary you are interested in. So these are the Z's I represented here. So Z1 is the argmin of the V on this part of the boundary, etc. And you take the potential here. You take the potential in the minimum at the minimum of V in the domain, and this difference enters the exponential here. I recall you that beta is 1 over kt. And then you have a prefactor which is also explicit using Hessians of the potential around Z and around X. And so if I plug this case in this dynamics, you understand that I can go very quickly from state to state because I jump out and then I go in a new state and etc. Okay, so it's a way to really get a very efficient simulation of the dynamics if this model is correct. I will refer to this formula as a harmonic transition state theory rates in the following because that's the way people are calling them in this field. And so the mathematical question we have now is the following. So we have basically two ways to simulate the exit from a metastable state. One which is a naive way, which is there, so which is just to follow the Langevin dynamics or overdump Langevin dynamics up to the time it leaves the domain. Okay, so this is method one. Method two is to use this jump Markov model parameterized using these Ihring-Kramers rates. And the question then is, can we relate these two ways, these two models? Okay. And let me do some very, so I'm a very practical guy, so I like to go back to the computer and to do some simulations to see what is going on. So I take a very simple case where I take these dynamics, okay, in 1D, which is discretized like that. So I guess you recognize a simple Euler scheme, very the simplest one you can think of. Over a time step of size h, the Brownian motion is just square root of h times the Gaussian. So we draw a Gaussian at each time step. And we go from xn to xn plus 1 using this formula. And this is the potential, and just I make a small drawing of the potential. This is how it looks like. So you have 3 wells here. And I will consider one well, which is in the middle. And I would like to see how the exit event from this well. So I will simulate the dynamics starting from the red point until the first time it touches one of the 2 grid points here. And I will register 2 things. I will record how long it took to go from the red to one of these green points. And second, I will record also, did I live through the left or the right points? Okay, very simple simulation. So this is, for example, what you obtain here. You start from 0 as a function of time, and here I left on the on the left, okay, through this point, okay. The temperature maybe enters here through the epsilon, okay. So the epsilon is related to the temperature of the system. And so now I do that 40,000 times, okay. So this is 40,000 simulations of this exit event. Each time I leave, I go back to the red point and I start again, okay. So I'll let you think a little bit about what we are doing here, and I will do the histogram of the exit times. Okay, so I don't know if you have an intuition of what I will observe. I stay trapped for a very long time, so what people expect typically, it depends on your background, but what people expect is an exponential law. Okay, we expect the time to live to be exponential. It's related to metastability. So indeed, when you plot this vector of lengths, length is the size of the time it takes to live. The histogram of the length is very close to an exponential. You can fit it to an exponential. Okay. Then I will do a slightly different experiment. I will look at the length of those points where I left on the right. Okay. So remember, there are two ways to live, right or left. I will only keep the times when I left on the right, and then I will only keep the points when I left on the left. Okay, and I will do exactly the same histogram. Do you have any intuition on what I will observe in terms of exit times? So it will be again exponentially distributed, but maybe what is a little bit surprising is that I will get exactly the same exponential law. So this is when I live on the right, this is when I live on the left, and these are the three of them superimposed, okay? So from a probabilistic viewpoint, it shows that if I tell you I live on the right or I live on the left, it has absolutely no influence on the law of the exit time, okay? So the conditioning, if I put it in math, the conditioning by the exit point does not influence the law of the exit time. In other words, these two random variables are independent. Okay? So what we learned from these very simple experiments are two things. Typically, if we are in a metastable situation, we expect the exit time to be exponentially distributed. That's the first take-home message. And the second one is that we expect also this exit time to be independent of the exit point. Okay? And these are very good news in order to go to our kinetic Monte Carlo model, as I will explain in a second. Any question on this experiment? Is it clear? I don't know if you are surprised at this, but it's not. Okay, it's very simple to do. I can send you the notebook. It takes a few minutes to run, and you have this very clear result. So to make a link between these two worlds, I mean the Langevin dynamics and the kinetic Monte Carlo model, I will go through two steps. One, which is to justify that there is a KMC model which is correct. KMC is for kinetic Monte Carlo. There is a kinetic Monte Carlo model which is correct for some rates, and then I will explain why the rates can be approximated using the Ehring-Kramers laws. Okay, so it will be a two-stage argument. So let me first formalize a little bit what we call metastability. Metastability, maybe we can start with this, can be seen as follows. So if I start in the state, okay, so I start in the domain here, and if I run the dynamics for a time t, conditioned on the fact that the exit time is larger than t. So numerically it means that I reject all the simulations which left the domain O between 0 and t. I only keep both simulations which stay inside. So it means if you are metastable, it means that I keep most of them. Okay, and I look at the law at time t of this process, and I send t to infinity. This will converge to a kind of local equilibrium within the state. Okay, so to metastable states are associated some kind of local equilibrium. Okay, which are called, so this is called the quasi-stationary distribution, this new. So it's a probability measure which is supported in the domain and which can be seen as a long time limit of the process conditioned on being trapped. Okay. Another way to see it, and this is why it's called the quasi-stationary distribution. It's almost stationary in the sense that if you start under the QSD, this nu, and if you go for some time t, conditionally on not leaving the domain between 0 and t, so the exit time is larger than t, you are again on the nu. Okay, so it's a kind of stationary state for my process, but again conditioned on being trapped. Okay, so that's the QSD. And if you are metastable, if you have a metastable exit, as I call it, the time to reach this equilibrium will be much smaller than the time to leave. Okay, so in a well, you will reach this local equilibrium way before actually leaving. Okay, so that's a very good news because it means that since we have a Markov process, the question becomes, how do I leave if I start under the QSD? Okay, because by the Markov property, you only need to know where what is the distribution at time t to understand the future. Okay, so that's the next slide. The next slide is if I start under the QSD, okay, how I will live. So how long it will take on where I will live. Okay. Before I go to that, I just go quickly on that. So here I'm saying there is a QSD. Okay, so there are mathematics to do here to prove that such a nu exists, to prove these results. Okay, but basically it works. Okay, there is no difficulty. It's very much related to spectral properties of the infinitesimal generator of my process. So it's related to PD at the end of the day, and so you can prove that such a QSD exists, is unique, and that you have actually even exponential convergence to this QSD. There is a spectral gap which comes into the picture. But let me go to what is interesting here, which is I've reached the QSD. I've been trapped for a sufficiently long time so that I can say that. And then the question is, how do I live? So how long do I take to live? Let's look at the probability starting from the QSD that I live after a time s plus t. And I condition on tau being larger than s. So it's like this is just the base rule. Okay? So here I did nothing. But here, what I'm doing is that I'm saying that at time s, since I've been trapped up to time s, I'm still on the nu. I'm still under the QSD. It's a stationary property of the QSD. So it means that the time to reach, the time to live is exactly the same as before. And so here, it means that this is exactly the probability starting from nu. So this nu is a law at time s, that tau is larger than t now. Okay, I hope this makes sense. It's really just the Markov property and the fact that nu is a quasi-stationary distribution. Okay, it's a probability that at time s, I am still on the nu. And if you have this functional, equality, you know that the probability that tau is larger than t will be an exponential minus lambda t for some lambda. And this shows the exponential property that I was observing in my experiments before. And if I look at the independent property that we also observed in the Python code, it goes the same way. So you have you look at the law of the couple of random variable, exit point, exit time. You condition by this, and here again it's the same argument. At time s, I'm on the nu. So this is just the probability to live through a part A of the boundary. And this product structure shows that x tau as a random variable is independent of tau. Okay, so this is the proof of what we observe numerically, if you want. If you start under the QSD, and if you are in a metastable situation, the tau will be exponentially distributed and will be independent of the x tau. Okay, and so this in turn implies that if I define the rates using this formula, okay, so I introduce a rate which is a kj, the rate associated with the exit through the jth part of the boundary, is the probability to live through this part over the expectation of tau. Okay? I define these rates and I plug these in the KMC model I've presented before. You remember that in the KMC model, the exit time, the tau KMC, was exponentially distributed with a parameter which was the sum of the k's. If I sum of the k's, I will get just 1 over the expectation of tau. Okay? And since tau is exponentially distributed, it means that the tau KMC has exactly the same law as the tau of the Langevin of the full model. Okay? And if you look at the probability for the KMC to live, I call it I before, to live through the ith part of the boundary. So it was ki over the sum of the kj, if you remember. And ki over the sum of the kj, if you do the math here, you will see that it's just a probability that x tau is in doj. In other words, the probability, the exit door that you select using the kinetic Monte Carlo model is exactly the exit door that you observe in the Langevin dynamics. Okay, so it means that you have rates here which are in some sense ideal rates that you could use in the KMC model, and this will give you exactly the same exit event as the one that you would have observed using Langevin, except that it's much cheaper to simulate these two guys than to simulate tau and x tau. I guess you understand the interest of this. It's numerically, it's very convenient. Well, these rates, you don't know them a priori, but then comes the question of, can these rates be approximated using the Ihring-Kramers laws? And this is something we've been working on quite a long time. And you can show that it's indeed the case, at least for the overdamped Langevin. So for the moment, this is all what I presented before is quite generic. You can use QSDs for any metastable Markov dynamics. It could be anything. This is very specific to the overdamped Langevin. Okay, we believe that it goes beyond that, but to prove it is not clear. So let's focus on the overdamped Langevin dynamics. So remember, the overdamped is just dxt is minus grad v of xt dt plus root of 2 beta minus 1 dwt. And beta minus 1, I remember it's kBt, okay, the Boltzmann constant times the temperature. And associated to these dynamics, you have a differential operator, which is minus grad v grad plus beta minus 1 Laplacian, okay, which is called the infinitesimal generator of my process. And if I put the Dirichlet boundary condition on the boundary of O, okay, you have actually an operator which has a compact resolvent, so it has a discrete spectrum, and you can look at the ground state of it, so the first eigenvalue on first eigenvector. The first eigenvalue, I call it minus lambda 1. I put a minus so that lambda 1 is positive. On the first eigenvector, I call it u1. And why I'm doing that is because this ground state is related to all the quantities I'm interested in. First, the QSD you can show is just the ground state, it's just u1, time exponential minus beta v, normalized. Second, the parameter of the exponential law, if I start on the new, remember that tau is exponentially distributed. The parameter of this exponential law is nothing but lambda 1. So the expectation of tau is 1 over lambda 1. And third, the probability to live through one part of the domain is the integral over this part of the domain of the normal derivative of u1 time exponential minus beta v normalized so that you have a probability density. So if you want the flux, the way you live is given by the normal derivative of u on the boundary, like a leaking flux, if you want. So u1 as a sign because it's an elliptic operator, so it's positive. So you have like a bubble, if you want, on the normal derivative of this bubble on the boundary, give you the way you leave the domain. So now we have formulas to work with, and we can ask ourselves how this kj, which is given here in terms of u1, how this is related to the formula I've presented before with this prefactor on exponential minus beta v, minus beta, the difference of energies. And it's something that we did with Doyan Lepetrec and Boris Nectou, and which has just been accepted to Journal of École Polytechnique. So you can show that these rates, these theoretical rates, indeed, in the small temperature regime, and for energetic whales, they go to what you expect, so the Arrhenius laws. Okay, so that's the result we obtain using techniques from semi-classical analysis, and so it's quite a technical thing. So maybe I just say a word about the way it works. So you see, we want to look at the small temperature, so large beta. So when you send beta to infinity, basically you get rid of this Laplacian. Okay, so you go to a singular limit because you erase the higher differential operator. And so the question is how you analyze in this singular limit, how you analyze the ground state in this singular limit. And it's very close to what people are doing when they look at Schrödinger. And this is h bar, okay? And they say h bar goes to 0. I would like to go from quantum to classical mechanics, okay? So that's the same kind of techniques that we use, okay? So techniques from Bernard Helfer, Johannes Jostrand, and people doing semi-classical analysis. Okay, so I think I will. Yeah, maybe this slide. One thing we are looking at the moment is, let's look at the entropic case. So let's look at the case where you have a domain like that with very small exit doors. Okay, what are the equivalent of the Irving-Kramers laws in this context? That's something we are looking at. So again, you have a metastable situation. So you have again a quasi-stationary distribution that you can define, which is defined with a mixed Dirichlet-Neumann boundary condition, because you have Dirichlet here on the exit doors, on Neumann there, because it's just bouncing back on the boundaries. And we would like to look at the limit when the exit doors goes to 0. We can define the rates, and so what we expect is to obtain rates like that. Okay, so this is proven now. This is not completely proven, but this is something we are working on. Try to find the equivalent of these rates for this so-called purely entropic case. Okay. And using this QSD approach, we can at least ask the question in a rigorous way. So I would like to finish maybe in 5 minutes about on numerics, going back to numerics. So how can we use what we learned, okay, to simulate the system efficiently? Okay, so let's forget about the math here. Just I would like to do an efficient algorithm. So if you think about it a little bit, so what we would like to use is to benefit from the fact that if we stay trapped for a very long time in the domain, we reach the QSD. Okay, so how we can use that numerically to accelerate the sampling of the exit event? That's the question that we would like to address. And so you have 2 questions associated to that. The first one is, how long should we wait so that we are close to the QSD? It's called the decorrelation time. So there is an estimate of the decorrelation time that we need to do. And the second thing we need to do is how to use then the underlying jump Markov process that we know is correct in order to efficiently sample the exit event. Okay, that's the 2 questions that I would like to go through. So for the first one, the idea is that we know that the law of the process at time t conditioned on the fact that you've been trapped from 0 to t. We know that this will converge to a stationary state, and that this stationary state will be the QSD. So we can try to use that numerically to estimate, if you want, how long it takes to reach the QSD. We look at the time it takes to have a stationary law here. Okay, so you have techniques to do that. The basic idea, if you want to do that, is to do many replicas of xt. So you have many of them. You run them, and when one is leaving, you kill it. Okay, and if you look at the one which remains, they are distributed according to that. And so if you observe a stationary state, you have ways to measure that, which are using averages and things like that. You say, I'm fine. The problem is that maybe if you go for a very long time, everybody will leave. Okay, so there is a trick, which is that when one leaves, you duplicate one which is still inside, because the one which are inside have the correct law. So it's called the Fleming-Vio process. So you send n replicas inside your domain. When one leaves, you jump on one of which is still surviving inside. Okay. So in this way, you always have n replicas running, and you can show that in the large n limit, on large t limit, you converge to the QSD, and so you can do diagnostics, convergence diagnostics based on that. Okay. So this is just one way to explain to you how you do in practice this. How you test in practice that you are going to the QSD before leaving. And then comes the next question, and I will finish with that, which is, once the QSD, the quasi-stationary distribution, has been reached, how I can use the underlying kinetic Markov process, kinetic Monte Carlo process, to accelerate the sampling of the exit event. And you have 3 ideas which have been proposed notably by Arthur Water and Danny Perez, that we now fully understand with this QSD point of view. They derived it using, physical intuition, and so our work was in some sense to formalize what they did. One is using a parallel architecture. In some sense, it's about parallelizing time. One is changing the potential, and one is changing the temperature. So I will focus maybe on the first one in the interest of time. how to parallelize time. Okay, that's the question that which is there. So imagine that you have your process which entered the domain O, and at some point you say, okay, I reached the QSD. I've been trapped for a sufficiently long time so that I can assume that the law of this point here is under this local equilibrium. What do? I take many guys which are under the QSD inside the domain. Okay. Again, the Fleming-Vio process I've presented before is a way to obtain such red points. So now I have here 7 points which are under the QSD. Okay. And now I organize a race between the 7 of them. So I simulate all of them independently on different CPUs. Okay. And I look at the first one which leaves. Okay. So the winner of the race here is this one because he left first the domain. All the other ones have been trapped up to this time. And you look at this event, so the time it took for this system to leave on the point where this guy left. And the question becomes, can I, from this, reconstruct the time it would have taken for the blue guy to leave? And can I also, from this point, reconstruct a correct exit point for these blue guys if I have waited for him to leave? Okay, that's the question. And remember, we know two things. We know that the exit time of all these guys is exponentially distributed because they start on the QSD. And we know that the exit time of all these guys is independent of the exit point. And maybe if you think about it, you have the answer. The thing you have to do is just to take the time it took for the first one to leave and to multiply by the number of replicas. Okay? Because if you have n exponential laws which are independent and identically distributed, if you take the minimum of them, if you multiply by the number of exponential laws, you get exactly in law one of them. Okay? So very concretely, you are on your big computer in Los Alamos. Maybe you have 100,000 CPUs. You send 100,000 simulations in parallel. Okay? You look at the first one which exits. It took for some time to leave. You multiply this by 100,000, and you have a correct sample of the exit time of the time it would have taken for the first one to leave. Okay, which is quite magic. It's really you parallelize time. In work clock time, the time it took to simulate this guy, okay, is divided by the number of replica that you use, 100,000. Okay, so that's quite effective. In terms of parallel efficiency, it's 1 if you want. So this step. So if you think of PDE, it's like wow. Okay, it's really magic. The overhead comes from the first part. I have to wait to reach the QSD. Of course, no free lunch. But this is quite effective. And then you wonder if the point where the winner of the race, I call it I, not here. The winner of the race, he left through this point. Okay, is it correct? The fact that you have independence between exit time and exit point means that the point where the winner of the race left is exactly the same as the point where the first guy would have left. Okay, I put it the other way around to explain a little bit. Imagine that there is a correlation between time and exit point. With this algorithm, you will favor exit points which would be correlated with small exit times. Okay, but they are independent, so there is no bias. Okay, so you get this exit point is correct statistically. It has the same law as the exit point that you would have observed for x1, but in the future, if you had waited for it to leave the domain. And I would like to insist that to use this algorithm, you just need two properties. The fact that tau is exponentially distributed and independent of the exit point. So you only need QSDs. We never use the Ehring-Kramers formulas here. Okay, you see? So that's a very appealing algorithm that you can use in many contexts. Well, there are two other ideas. I will not go through them. One which is to modify the potential, to raise a little bit the potential inside the well and to correct for this bias using the Ehring-Kramers laws. So this works only with the Ehring-Kramers laws. And there is another one which is to raise the temperature and to correct for the bias that you introduce by raising the temperature, again using the Ehring-Kramers laws. Okay, and okay, that's so to summarize, I mean numerically, there is this parallel replica which only use the QSD, and these two algorithms hyperdynamics and temperature accelerated dynamics use the fact that you have Ehring-Kramers formulas which are good approximation of the exit rates. Okay, and all these, of course, they require to have good metastable state in the sense that when you enter a state, most of the time you decorrelate before leaving. You reach the QSD before leaving. Otherwise, you don't gain anything. You cannot do anything. Okay, so you benefit from this using these techniques. Okay, that's. So there are many things we are working on. One is a problem maybe which may ring a bell here is how to optimize the definition of the states, how to get the best states. Okay, and since we have a spectral interpretation of all this stuff, it's an optimization on the spectrum. It's an optimization of a functional which depends on the spectrum. Sorry. So we have Dirichlet problem on the domain. We have the first two eigenvalues. 1 over lambda 1 is the exit time, and 1 over lambda 2 minus lambda 1 is the time to reach the QSD. So we have to optimize the ratio of two times, if you want. We would like the time to exit to be long, and the time to reach the QSD to be short. Okay, so there is a ratio of eigenvalues to optimize as a function of the domain, and so we do shape optimization. So that's an example of things that we are working on. This has been done by Noé Blassel. He just defended his PhD in December. That's it, I guess. So if you want to learn more on that, so this first paper in the Faraday discussion is really presenting things in a gentle way without the hard mathematical machinery. This is the mathematical machinery typically that I presented in the theorem, and these are other results, and these are more general, review papers or a book on, how mathematics can be used in this molecular dynamics world. And so, if you're interested in the topic in general, these are things you can look at if you are interested. I thank you for your attention.
Thank you for this fascinating talk. So I suppose there will be many questions. Looking for questions. If there are no questions, I will ask a question. Okay, Stefan is there. Stefan,
the range of application is broader, but I'm not sure how broad this is. Can you comment on what are the conditions to be able to?
Yeah, so the basic setting that we need at the end of the day is a Markov process. So we need noise. Okay, so I don't know if you have. So we need noise somewhere because we need transitions to be related to some combinations of events. For example, for Freddy Boucher doing it's about having a heat wave somewhere, and this is a combination of noise. So noise is coming from turbulence. I stop here here because, and in this context. And okay. But as soon as you have a Markov process and you have this metastability feature, which is the fact that you remain trapped in some state before going to another one, basically you are in business to look at these algorithms and these techniques. What is specific to MD is maybe the dynamics are not anything. We have these Langevin dynamics, and sometimes we use them to do the math. But the concept of QSD and the parallel replica I've presented, for example, these two things are very, very generic. I mean, people have been working on the existence of QSDs, and for the moment, for any Markov process we could think of, there is a QSD in a domain. So it's something which is very generic. And I think that I convinced you also that the consequence of the existence of a QSD, so the fact that the exit time is exponentially distributed and independent of the exit point, is also very generic. I need nothing more than the existence of the QSD. So yes, it's very generic, and it can be used in other contexts. And it's the same for the rare event simulation algorithm that we are using to go from one state to another one. They can be used as soon as you have a small probability to estimate somewhere. You can, for risk analysis, for things like that. People are using this algorithm in other contexts also.
Thank you. So the distribution of exit times is exponentially distributed.
Yes.
But that means that there is also a typical exit time. There is a There, yeah. And this typical exit time, how does it scale with the size of the system? For example, would it be some exponential of the number of molecules, or have you looked at that?
Alors, the expectation of tau, how it scales with the physical parameters. So what I can say, so, alors, what we could look at are the Arrhenius laws. So we know that the rates, at least for an energetic barrier, they scale like that in the small temperature regime. So it's a way to understand, to answer your question. So you see that in the small temperature regime, you see that the rates, so for example, the typical exit time is 1 over the sum of these rates. Okay. You see that they scale like you have a competition between the energetic barrier that you have here, and beta minus 1, which is kBt, which is the thermal energy. So you have to compare the height of the barrier and kBt, which is a kind of the energy coming from temperature. And so this is one scaling which is there. And another thing which is in front of everybody here are these terms that I did not really comment on. So this determinant of the elevation of V at x1 is a measure of the size of the domain. And this, the determinant of the elevation of V at the saddle points, and you see that there is here the absolute value of the negative eigenvalue at the saddle point, because you have a negative eigenvalue, because you have a saddle point, so you have a direction when it goes down, on all the other direction when it goes up. So this is, in some sense, these two terms are a measure of the size of the window on the boundary. So it's not the same to go for a given energy level, V of Zj, is not the same if it's very narrow region or if it's a very large region. Okay, and it's not the same also if you have a very steep, a very steep negative, unstable direction, or a very smooth, a very soft, let's say, unstable direction. So here you have some answers to your question, okay? And in particular, for the number of particles, it depends on how V depends on the number of particles. So typically it's extensive, and typically when V is large, these terms will scale like n, but it's really the relative difference between the two. So it depends, I guess, on the system, how this will scale and the number of particles.
But that's probably easier to study that than to study the entropic trapping.
The entropic trap is a little bit, yeah, it's for the moment we are struggling a little bit. I mean, mathematically it's a mixed Dirichlet-Neumann boundary condition. So you have here, at the point where you go from Dirichlet to Neumann, you have some singularities. So first there are some technical problems related to the, and yeah, so I don't know if it's easier or more difficult, but what is true is that we have less tools. So here we had tools from people working on semi-classical analysis, so it was like techniques on the shelves that we can use. Here we are more in the dark, so we are, trying to understand this narrow escape, so-called narrow escape regime by ourselves, because there are not so many mathematical works up to now. That's.
Are there questions? Yeah.
Maybe just to continue the discussion, because I think it's kind of related. So when you show this example, you find that in the end the conditional exit times are the same for both the right and
yes.
the left solution. But one could intuitively expect that it's more likely to go out from the right because
yes.
the potential barrier is
yes.
lower.
Yes.
So what's the physical explanation?
So this is correct. Huh? So the time to live on the right is K1 over K1 plus K2. It's what I wrote here.
Okay, so it's just the shape of the curve.
Doodle.
Okay.
So it's K1 over K2, and you can and you remember that K1 is essentially exponential minus beta, this difference of energy, which is much smaller than that. So you will indeed have a higher probability to live on the right than on the left. And so if I go back to my simulations, you observe that the probability to live on the right is about 80% for the parameters I've taken, okay? And you can compare this 80% to what is expected from, from the theory, and you see it's very close. I mean, it's this limit is very well approximating what is observed numerically, even for temperatures that are not so small, because you see it's 80%. It's not 0.999. I have only 80% probability for this setting to go on the right, and it's already well approximated with this regime. So you're right. So the probability to live on the right is higher, but the time to live is the same. That's a little bit, for me at least, when I worked on that first, it was like, no, it will take more time to go on the left because it's higher. No, but conditionally on the point, it doesn't change anything, which is a little bit maybe surprising.
Maybe a question on the other two methods you were mentioning
Yes.
at the end, which were to change the potential or change the temperature.
Yes.
It's like sort of rescaling we are introducing, basically, right?
Exactly.
So you move-
Exactly. It's like a rescaling because, okay, sorry, please.
Yeah. So maybe you can mention briefly how you do the rescaling.
Yeah.
Because, you can do that. I don't know. It's data driven or it's.
Yeah.
you've
So
done some-
here we really rely on the fact that we know that the exit rates have formulas. So in instance, we have two families of exit rates. The exit rates on the original potential V and the exit rates on the biased potential V plus delta V. Okay? So here I write an exit rate on the original potential V. Okay? And if I change V to V plus delta V, what will happen? It will change this term here. I will have a V plus delta V and a V plus delta V here. Bon. The point is that we modify the potential only inside the well. That's really important in these techniques. So we don't touch on the potential on the boundary. So if I go back to my formula, it means that this V of Zj will remain the same. I will only change this V. Okay? So when I do the ratio, so if I look at the probability to live through the region J, it will be the same for V and V plus delta V. So I do not change. So what I'm saying is that I do not change the relative probability to live through the different doors if I just change the potential, the minimum of the potential. So if I go back to my Python simulation here, if I change this minimum, I raise it a little bit. Okay, I do that. I will still have 80% on. Okay, that's one thing. Of course, I've changed the time, but I know how I change the time. I change it by basically the average of exponential minus beta delta V. Okay, so I have a way to find the real time I would have needed to.
Go back.
Yes. So that's quite easy to go back actually with these techniques. For temperature, it's more complicated because temperature you completely screw up the relative probability of the different exit doors. At higher temperature, because of entropic effects and all, so you change the relative probability. So you have to do so-called Arrhenius plots and to observe many exits at high temperature to infer what you would have observed at low temperature. So it's a little bit more technical. I can explain it to you, but it takes 10 minutes. It's more complicated. But basically, it's the same ingredient. I look at the ratio of the case at temperature T plus at T high over T low, and I do the math. That's
How to accelerate the particles so that they come out.
yes, so that's basically it's the idea. How can I accelerate the exit event? And what comes to mind first maybe is, okay, I just crank up the temperature, okay, so it will go out, or I change the potential so that it's less difficult to live. Okay, it's what I've said before. There is KBT on V, so I erase KBT or I go down the V. But that's the two ideas. That's not.
Okay, any other questions? Okay, so maybe it's a good time to congratulate
Thank you again for listening to me.